Good evening, everyone. Today, we embark on a journey into the realm of forensic science, exploring a groundbreaking technology that has revolutionized investigation. The power of fluorescent carbon dots. Tiny carbon-based nanoparticles, usually less than 10 nanometers in size. Despite their small size, they pack a powerful punch with their unique optical properties. These dots emit strong fluorescence when exposed to UV or visible light, making them incredibly useful in forensic investigation. One of the most promising applications of carbon dots is in the detection of latent fingerprints. Traditional methods sometimes fall short, especially on complex or multicolored surfaces. However, when we apply carbon dots to fingerprint residue, they emit a bright fluorescence that makes even the faintest prints clearly visible. This non-destructive method preserves the evidence, allowing us to conduct further analysis without compromising the integrity of the fingerprints. But the usefulness of carbon dots doesn't stop at fingerprints. They also excel in detecting biological stains like blood, saliva, and semen. When these stains are treated with carbon dots, they fluoresce brightly under specific lighting conditions, revealing even the smallest traces. This high sensitivity is crucial, especially in cases where biological evidence is minimal. In document examination, carbon dots can differentiate between various ink and identify alteration or forgeries. They interact with inks and paper, emitting different fluorescence patterns that can uncover discrepancies invisible to the naked eye. This capability is invaluable for authenticating documents and ensuring the integrity of legal evidence. Carbon dots are also making strides in detection of drugs and explosives. By functionalizing these dots to bind with specific substances, we can detect minute quantities of hazardous materials based on changes in fluorescence. These applications is vital for crime scenes and security checkpoints where quick and accurate detection can prevent significant harm. Lastly, in trace evidence analysis, such as fibers, hair, and gunshot residue, carbon dots provide high-contrast imaging. This helps forensic experts to visualize and identify tiny particles linking suspects to crime scenes with greater accuracy.
Next, I am going to present about the operation of fluorescent carbon dots. To visualize latent fingerprints using fluorescent carbon dots, we have to apply this carbon dot to the surface containing the latent fingerprint using a brush method, ensuring even coverage across the entire surface. The next step is to illuminate it with UV light. Under the UV light, the carbon dots will fluoresce, thereby making the latent fingerprint visible. Finally, capture the fluorescent fingerprint using a suitable camera or imaging device, ensuring the device is capable of handling UV light photography. After capturing the images, proceed with fingerprint analysis.
Advantages of fluorescent carbon dots in forensic science. These tiny yet powerful materials are truly revolutionizing our field. First off, one of the primary advantages of fluorescent carbon dots, or CDs, is their high sensitivity. CDs can detect extremely small traces of substances, which is crucial in forensic investigations where evidence might be minimal. Another key benefit is their strong fluorescence. CDs exhibit bright and stable fluorescence, making even the tiniest samples highly visible under UV or visible light. This significantly enhances the accuracy of our analysis. Additionally, CDs are incredibly versatile. They can be tailored to target specific substances, allowing us to detect a wide range of forensic materials, from blood and drugs to other biological samples. Speaking of biological samples, Another advantage is their biocompatibility. CDs are non-toxic and safe to use with biological evidence, which is vital for preserving the integrity of the samples. We also need to highlight their durability. CDs are stable under various environmental conditions, ensuring they perform reliably during forensic investigations, regardless of the setting. The ease of synthesis is another benefit. CDs can be created from various carbon sources through simple and scalable methods, making them easily accessible for forensic use. Finally, CDs offer multifunctionality. They can be used for imaging, sensing, and as contrast agents in microscopy, serving multiple roles in forensic science. To sum it up, fluorescent carbon dots are highly sensitive, strongly fluorescent, versatile, biocompatible, durable, ease of synthesis, and multifunctional. These advantages make them an invaluable tool in enhancing the detection, analysis, and interpretation of forensic evidence.
Fluorescent carbon dots, also known as CD. These fascinating nanomaterials have gained significant interest due to their unique optical properties, low toxicity, and potential application in various fields like bioimaging, sensing, and drug delivery. However, several challenges and limitations obstruct their broader application and advancement. Here are some of the key issues. Let's start with the first challenge, synthesis and reproducibility. The synthesis of a carbon dots often lead to a heterogeneous mixture with a varying size, shapes, and surface functionality. This variability can significantly impact their optical properties and performance. Additionally, achieving consistent and reproducible synthesis method is difficult. Even small changes in synthesis conditions such as temperature or precursor concentration can result in significant variation in the properties of CDs. Next, we have quantum yield and stability. Many CDs exhibit low quantum yields, which is a critical limitation for application in bioimaging and sensing. Furthermore, CDs can suffer from photobleaching, where prolonged exposure to light degrades their fluorescence. This limits their use in the long-term imaging and sensing applications. Surface functionalization is another significant challenge. Proper surface preservation is necessary to improve the fluorescence property of CDs, but achieving efficient and stable preservation is difficult. Additionally, functionalizing the surface of CDs to impact specific properties of target-specific applications can be complex and may affect their fluorescence behavior. Now, let's talk about toxicity and biocompatibility. While CDs are generally considered to be less toxic than other nanoparticles, there are still concerns regarding their long-term toxicity and biocompatibility, especially for in vivo applications. Understanding the biodegradation pathway and potential accumulation of CD in biological systems is essential to ensure their safe use in medical applications. Moving on to optical properties, CDs often exhibit broad emission spectra, which can limit their use in multiplex imaging applications where narrow and discrete emission peaks are desired. Additionally, the fluorescence of CDs can be sensitive to changes in pH, which can be problematic for applications requiring stable fluorescence under varying environmental conditions. Scalability is another significant challenge. Scaling up the production of CDs from laboratory to industry scale while maintaining their desirable property is difficult. Furthermore, developing cost-effective methods for large-scale production of high-quality CDs is necessary for their commercial viability. Lastly, considering the environmental impact, the environmental stability and potential ecological impact of CDs need to be truly assessed. Understanding their behavior in different environmental conditions is crucial for their sustainable use.
Next, I will present our last point in this topic, which is comparison between fluorescent carbon dot with a conventional method for fingerprint detection. While both methods have their application, fluorescent carbon dots offer several distinct advantages that make them the superior choice for forensic fingerprint detection. Let's start with sensitivity and resolution. Fluorescent carbon dot exhibit exceptionally high sensitivity, capable of detecting even the faintest fingerprint. This is due to the ability to pick up minute traces of sweat and oil left by the finger. Additionally, they provide unparalleled high-resolution image, making it easier to discern fine details and rich patterns in fingerprints. In contrast, conventional methods such as 9-hydroxy cyanoacrylate filming and fingerprints powder have variable sensitivity. For example, cyanoacrylate, known as superglue fuming, adheres to oily residue. However, this method might not be effective in detecting faint or partial print, and the resolution may not match that provided by fluorescent carbon dots. Next, let's discuss visualization. Fluorescent carbon dots emit strong fluorescence under UV or visible light, significantly enhancing the visibility of fingerprint. One of their key advantages is multicolor detection. They can be engineered to emit different colors, which allows for the detection of overlapping fingerprints, providing a clear distinction between different prints. On the other hand, conventional methods rely on color change reaction or physical adherence. For instance, nitrogen turns purple when it reacts with amino acids, while fingerprint powder sticks to sweat and oil residue. Typically, only one color is produced, which might not be as effective in differentiating overlapping. Moving on to application and use. Fluorescent carbon dots can be easily applied using a spray or dip method, simplifying the fingerprint detection process. Importantly, this method is non-destructive, preserving the integrity of the sample for further analysis. Conversely, conventional methods often require multiple steps, including chemical treatment and development process. Methods such as cyanoacrylate filming involve several stages to develop the paint. Additionally, some conventional methods may alter or partially destroy the sample during the process, making it difficult for further analysis for retesting. Now let's consider the environmental impact. Fluorescent carbon dots are eco-friendly as they are made from carbon-based materials. This makes them more environmentally friendly compared to some chemical reagents used in conventional methods. They pose fewer health and environmental risks. In contrast, some conventional methods use hazardous chemicals such as iodine fuming and silver nitrate. These chemicals pose environmental and health risks, and their disposal must be managed carefully to prevent environmental contamination. Lastly, let's talk about cost and accessibility. Fluorescent carbon dots are generally cost-effective as they can be produced at a low cost compared to some traditional regions. As their technology continues to develop, their availability will increase. Conventional methods are well established and widely available in forensic labs worldwide. The cost of this method can vary, with some being expensive like fingerprint powders and other more costly like advanced chemical reagents. However, their widespread use and long history make them highly accessible. In summary, fluorescent carbon dots surpass conventional methods in several key areas that offer high sensitivity, high resolution, multi-color detection, easy application, and environmental benefits. These advantages make fluorescent carbon dots the superior choice for modern forensic fingerprint detection. Thank you for your attention. I hope our presentation highlight why fluorescent carbon dots are the best option for fingerprint detection and adding your knowledge on these fluorescent carbon dots.